Ladies and gentlemen, good afternoon. Thank you for joining us at Nissan Motor Corporation Media Briefing. We appreciate your kind participation. We are going to have a briefing on breakthrough in e-power dedicated engine achieving 50% thermal efficiency. Because of the pandemic, we are going to host this conference based on internet. This will be recorded and will later be updated on the YouTube channel for Nissan Motor Corporation. We look forward to your kind understanding. I'll be serving as the moderator and with the global communication. I would like to introduce the participants from our side. Responsible for Powertrain Technology Development, Senior Vice President, Mr. Toshihiro Hirai. And also Powertrain E-Train, responsible for Powertrain, Deputy General Manager, Mr. Tadashi Tsurushima. The speakers will not be using a microphone. However, we have maintained sufficient social distance and we have introduced sufficient ventilation within the conference hall as well.
Ladies and gentlemen, good afternoon. Thank you for taking your time to join your session, irrespective of a lot of restrictions given by COVID-19. As you have seen, we are working on achieving 50% thermal efficiency enhancement in the next generation e-power dedicated engine. We have this visibility. So let me take this opportunity to talk about. I'm in charge of powertrain development, EV development. My name is Hirai. The person beside me is Tsurushima-san, who is in advanced technology engineering team, and he will be joining me to make a presentation. I would like to spend the first 30 minutes on the presentation. Now, I would like to talk about the entire picture of the carbon neutrality that Nissan is pursuing, as well as the electrification strategy based on EV and e-power. I would like to elaborate on the approaches that we are taking on those fronts. Afterwards, I would like to talk about enhancing thermal efficiency by 50% and the progress. Tsurushima-san will elaborate you on this point. Lastly, I would like to talk about the electrification promotion and producing better and attractive products and technologies. Now, let me start by what we are doing in order to pursue carbon neutrality. Last month, Nissan announced the carbon neutrality goal for 2050. In 2030s, in early 2030s, every all-new Nissan vehicle offering in key markets will be electrified. As a specific example, these are the 4 actions that we are taking, and that has been announced. From the left, we have greater energy efficiency of our e-power electrified powertrains. With a more thermal efficient EV, we are innovating the technology of battery and develop a battery ecosystem to support decentralized renewable energy generation and greater energy and material efficiencies during the manufacturing process. These are the 4 areas or actions that we are taking, and today I would like to focus on e-power with the better energy efficiency. Our approach to carbon neutrality is based on life cycle assessment. It's an entire life cycle assessment. It's not only about introducing carbon neutral vehicles. We are looking at the materials, mining or life cycle, and the entire value chain. Across the board, we would like to reduce the CO2 emission throughout the life cycle, including the sourcing of the materials. As part of the electrification strategy, as you can see, renewable energy penetration will, as we see this, we would like to expand the application of battery EV, but penetration of renewable energy will take time. And when it comes to charging infrastructure and electrification, it will take time. Therefore, in this process, carbon free, CO2 free is the area where we would like to contribute. And to this end, we are using e-power as one of the pillars of electrification. In early 2030s, we would like to electrify all new Nissan vehicle offering. And as an action to penetrate the market with this technology, we will not only introduce electrified vehicles, but we will make sure that new values of electrified vehicles, free, flexible, and powerful. These are the things that we would like to communicate and make sure the customers understand. Let me elaborate on the approach to EV and e-power, which is part of electrification. On the horizontal axis, you find the evolution of powertrain, how the powertrain will be developing. This is on the timeline. And on the vertical axis, you see a value like CO2 emission reduction. What will be the scope of the impact of the technology is visualized on this. From the left to the right, you see natural aspirated engine. What we see today, IC from IC internal combustion engine, we are seeing downsized turbo with a high thermal efficiency, which we see in larger number today. 3 years ago, we introduced VCR. This technology is one of the downsized turbo engine with a high thermal efficiency. This was the world first technology that we introduced. So our technology to enhance the thermal efficiency is combined with battery EV, which is driven 100% by motor. By combining these technologies, we produce e-power, which is in the middle of this chart. We use e-power and zero emission, which is a battery EV. Based on these two pillars, we are driving electrification. In other words, as you can see in the small letter, mild hybrid, plug-in hybrid, where other OEMs are adopting in large numbers. With regards to these technologies, we will use alliance assets as a complement. But one of our pillars of engineering is e-power and zero emission rather than working on mild hybrid. As I said, battery EV and e-power, based on these two pillars, we are approaching electrification. But 100% motor driven is the same. Is we can say the same thing. The question is how to generate electricity. That's the big difference. Battery EV. In the case of battery EV, we use power from the utility company, where e-power, gasoline, is used to generate electricity. This is one big difference between battery EV and e-power. And we are going to use these two technologies to reduce the CO2 and LCA, and this is the visualization of the efforts. While we manufacture vehicles, we emit CO2. And in order to generate power to drive, the CO2 emission is in yellow, and CO2 emission, which is emitted during driving, is in orange. E-power, the CO2 emission during driving is much less than ICE. However, battery EV is zero emission. But the CO2 emitted during the manufacturing of the vehicle, or the power generated to drive the car, to this end, we need to emit CO2. And depends on the electricity mix. But as of today, you see this ratio is pretty high. So that is why people saying that battery EV CO2 performance may not be as good as people say if you look at it from the LCA viewpoint. However, if you look at these two pillars of electrification, we are developing technologies to reduce the CO2 on both aspects. E-power, you see the orange one, which is the CO2 emission during driving. In order to reduce this, we are maximizing the thermal efficiency. With regards to EV, it's no CO2 is emitted while driving, but CO2 is emitted when the power is generated. But we will reduce this level, and CO2 emission to produce battery is being reduced. And to this end, we are trying to reduce CO2 emission by using the recycle the materials or reuse the battery. This is how we are trying to reduce the CO2 emission on those fronts. Now, let me provide the details. Today, for zero emission, I will be very brief about zero emission. I would like to have another opportunity to talk about zero emission. This is about how the EV has been evolving. As you can see, Nissan Leaf, the latest generation came in 2017, and since then, Leaf E Plus, and last fiscal year, we unveiled Aria, where battery capacity is increased from 40 kilowatt hour to 90 kilowatt hour, and electrify powertrain has more power. This is how we deliver better driving performance and other performance. The latest Nissan Leaf has an autonomy of 400 kilometers or over an area with a 90 kilowatt hour. It drives for 600 kilometers, although this is internally measured. This is the autonomy which is possible. So EV will be sufficient to use in your daily life. That's where we are today. In addition to this, battery circulation economy is what we are trying to develop. As the EV penetrates the market, there will be increasing number of batteries that you'll find in the market. So by recycling the battery, we would like to deliver new value while we reduce CO2 emission. With the sales of vehicles, if we sell vehicles are no longer only means of transportation. It will be a mobile storage battery, so it will be part of the energy solution. We call it V2X. We connect vehicles with house, or connect vehicles with building, or connect vehicles with blue switch, or battery storage. Storage batteries used for emergency. So as you can see, there are a lot of values of EV as a source of power. This is how we are going to enhance the value added of EV and reuse and repurpose, which is the second one. Battery. After the end of life of onboard battery, we still can use battery for other purposes because we have better performance battery, so we can reuse it. For example, smart grid is what we can use the old battery for. As if we use wind power generation, which is one of the renewable energy, and the solar power generation as a source of grid, we can use end of life battery, onboard end of life battery. In order to promote the use of it as a source of grid power, we are all talking to utility companies, and recycling is another one. With regards to end of life battery, we will make sure we break it down to nickel, cobalt, and lithium raw materials so that we can reuse it to produce new batteries. So we are going to make sure we create a battery circular economy or society. Now let me talk about our subject today, e-power. So what is e-power? Let me define e-power. You see the battery EV at the top, and at the bottom you find e-power. As you say, battery EV has a big battery, and using the power from the utility company, we charge the vehicle. As a result, motor drives the vehicle 100%. This is a battery EV. In the case of e-power, motor is will be used as a drivetrain, and we use the common parts with battery EV. The battery capacity is 1/50th of the battery EV in the case of e-power. So we generate power using gasoline as a fuel. So the utility company is within the vehicle, but the car itself is driven by motor, which is identical to EV. Thanks to 100% motor drive, e-power is as attractive as EV, powerful and smooth driving or acceleration compared with the traditional hybrid. Standing start and acceleration is better, and smooth acceleration is highly appreciated by the users. As you can see on the right, we find overwhelmingly quiet. In the note with note, it is equivalent to D segment when it comes to quietness and riding comfort. And this is well received in the market. On the left, you find smooth and powerful acceleration. You are seeing how the car drives. Thanks to the motor's high rotation or high driving performance even at the low speed with an excellent control from the standing start to acceleration, it's very smooth and powerful. In addition, overwhelmingly quiet is on the right hand side. With the new Nissan Note, the unevenness of the road surface is sensed and the vehicle automatically grabs the road noise, and with the road noise as high, it generates power. When the road noise is quiet, engine will not be used to generate power. Through this careful control, we provide a very quiet cabin. This is how it works. Next page, please. And this is further evolution of e-power. How far will this dedicated electricity generator engine will be developed? This is what I would like to describe. I use the expression of thermal efficiency when the gasoline, if the energy that the gasoline provides is at 100%, our existing ICE only uses 60% for exhaust, friction, and other purpose. So the only 40% is used to drive the car. With the latest engine, only 40% is used. In the past 50 years, we have increased efficiency of thermal efficiency from 30% to 40%. But in order to increase by 10 percentage points, it took 50 years. But in e-power, in the several years, we can increase it to 50%. That's the target of the engineering community. And 50% thermal efficiency. What does this mean precisely? Why did we set 50% thermal efficiency? It sounds good. That's one reason. And though we have been involved in ICE, and we believe that the ultimate goal or challenging goal is 50%. That's another reason. By changing the role of internal combustion engine, we may be able to achieve 50% of thermal efficiency. And with this in mind, we have been setting this goal of 50% thermal efficiency. But as I said, if you look at the CO2 emission through life cycle assessment, this is e-power. If e-power achieve 50% thermal efficiency, as of today, with the existing electricity mix in Japan, the EV CO2 emission will be equivalent to this one. Needless to say, EV, as I said, can reduce the CO2 emission by using renewable materials or recycling materials. By using reusing battery, we will be reducing the CO2 emission. And this level corresponds to 50% thermal efficiency. So in the process of EV evolution, we need to attain this 50% of thermal efficiency. So that is why we are taking on the challenge to achieve 50% thermal efficiency. Now I would like to hand it over to Tsurushima-san about how we are attaining 50% thermal efficiency.
では次に、熱効率
Thank you very much. Next, I would like to talk about our approach to achieving 50% thermal efficiency and where we are. My name is Tsurushima. I'm with the e-powertrain development, and I would like to talk about this topic. I mentioned that in 10 years, we'll be improving the thermal efficiency to 40 to 50%. So improving thermal efficiency for ICE engineers is an ever unchanging topic, emission. And conventional gasoline engine is now delivering 40% thermal efficiency. But as was mentioned, the 50% thermal efficiency is already viable at the risk RD level. But when it comes to commercial ICE model, this can also present several issues. In order to improve efficiency, we need to improve theoretical efficiency, and also various improvements will be necessary. In the case of ordinary ICE, you have to drive the cars in a very broad environment. So therefore, we need to come up with optimal specification for each driver, and also we need optimal settings. Settings will vary from driver to driver. So through trade-off, there's some obstacles which we are not able to overcome. So achieving 50% thermal efficiency for ICE cars can be a very challenging ultimate challenge. So this might not be able, you might not be able to envision what this is about. So let me try to talk about it. In 2001, Ichiro achieved 357. This is equivalent to the efficiency of the engine. So 50% throughout the season means that you have to be hitting 50%. That's the batting average for Ichiro. So even for Ichiro, 50% batting average would be a very lofty goal to achieve. So that's the caliber that we're talking about. So 50% target in terms of thermal efficiency is extremely difficult. And I think you can appreciate how challenging this target is. Now, for Nissan engineers, this 50% target, have we given up on that? No, that is not the case. For Nissan, we have e-power, and e-power has a different role. The role of e-power has drastically transformed. So Nissan engineers, against this change in the role of engines, has seized this as an opportunity to improve thermal efficiency, and we are now envisioning fixed point operation in addressing this challenge of 50% thermal efficiency. So next, let's talk about why is it that we were able to improve fuel efficiency in e-power. So why e-power was able to improve the fuel efficiency? For one thing, it's the way the engines were used in e-power. Please take a look at the graph. This shows you conventional ICE and e-power. We show you how the difference is in terms of how these are used. The left-hand side shows conventional ICE. It shows you and the right-hand side shows the frequency of e-power and conventional ICE. We show you engine torque and also engine speed in vertical and horizontal axis. Now you'll see an eye socket-like area. This shows you the best thermal efficiency area. The blue bubble, the size of the bubble shows the time in which the engine is utilized. So if we look at the distribution of the bubble between conventional ICE and e-power, the distribution is different, which means that the use of the engine varies from the two. In the case of conventional ICE, engine and tires are connected, so therefore low speed and idling, engine thermal efficiency, there's deviation from the best thermal efficiency area. In the case of e-power, there is no link between the tire, which means that you're able to have the best thermal efficiency area throughout all times. So that is the reason why the e-power fuel efficiency is better. Next, why is it that e-power specialized design can achieve 50% thermal efficiency? Let me try to explain that as well. Left-hand side shows the torque on the vertical. This shows torque and engine speed, and the blue shows the best thermal efficiency for the conventional, and the red. With regard to the next generation e-power, which we're developing, the acceleration will be ensured by the battery. So therefore, we will not have to have no operation in torque. And also, we'll be able to cut back on the maximum rotation, which means as far as the engine structure is concerned, we're able to have, without having a very broad operation, we're able to have the best thermal efficiency point. And we're able to have the maximum output. Furthermore, the right-hand side shows you the e-power, the future evolution of the e-power. The battery technology will have evolved, and battery output is basically used to cover power needs, even during acceleration at high speeds, which means that we'll be able to have a fixed point operation. In that case, the output will no longer have to be considered, which means that we're able to have high compression so that we can focus on the engine, which means that we're able to realize high thermal efficiency as a result of that structure. Next. In order to achieve 50% thermal efficiency, what are some of the key technologies? The left-hand side shows the compression ratio and the theoretical thermal efficiency. This shows you copper, which means that the heat is translated into energy in a very efficient manner. As this ratio is high, it means that the efficiency is high. If we are to achieve 50%, it means that we need to improve the theoretical efficiency. We need high compression ratio, and we also need to increase specific heat ratio for that purpose. Now, with regard to high compression ratio, we need technology that mitigates knocking even at high compression ratios. And we're able to achieve early closing Miller cycle. We're also able to strengthen in-cylinder gas flow rapid congestion, and we have adopted cooled HER. Second is to increase specific heat ratio. Of course, we need to have mass HER and lean combustion. So therefore, we need technology that can stably burn even with high HER or lean combustion. So in order to achieve high HER and lean combustion, we need stable ignition system. So therefore, we need to strengthen in-cylinder gas flow to ensure combustion, and also we need to achieve high energy ignition system as well. Now, today, I would like to introduce to you the in-cylinder gas flow structure that ensures combustion. This is the key technology. So now let's focus on high HER and lean burn. These are technical issues for achieving high dilution combustion. What you see on the slide or the video is the combustion, ignition in the in-cylinder. And we're using an endoscope video to show you. It's like an endoscope, and we have visualized this process. To the left-hand side, it shows you the ICE. The right-hand side shows high diluted. Compared to the theoretical ratio, the air is 2 times. So therefore, this is lean combustion. Now, in this video, you'll find that the combustion is still robust. In the case of lean burn or lean combustion, in particular, in the initial ignition, the speed is very low. Initial flame nuclearation is very slow, as you can see. Now, furthermore, on the right-hand side, we're showing you where the air is 2 times. This is the initial flame. This is the initial flame nuclearation not working out very well, and the combustion is very slow, and we end up with a partial burn as a result of the failure in the initial flame nuclearation. So, as a result of visualization, high HER lean burn requires strong initial flame nuclearation. So, initial flame nuclearation is the key. So, having stable ignition and having good nuclearation, this really represents the key to the success. Here, we show you the technical issues for achieving high dilution combustion, high HER, and lean burn. This is the initial flame nucleus. This is where we have a good combustion. And the plug, the ignition plug, we have this appropriate flow velocity to the spark plug, which means the discharge channel in the C letter shape, discharge channel is working. So as you can see, if the discharge channel is extended in appropriate manner, then they're able to supply energy. There's sufficient space to offer energy, which means that stable energy of the supply can be done, which means that the initial flame nuclearation can be achieved. Now, against this backdrop, the left-hand side shows where the ignition plug flow is very slow, where the flow velocity to the spark plug is slow. If that is the case, then the discharge channel will not be extended, which means that energy supply will be insufficient. So therefore, initial flame nuclearation cannot be done. On the other hand, the right-hand side shows where the flow of the velocity is too high. High flow velocity means that this puts out the ignition, which means that initial flame nucleation cannot be formed. So therefore, the engine will vary from cycle to cycle, so there are always variances. But it's important that we reduce the variances and offer stable flow, so that initial ignition can be supplied. It's important that we have stable discharge channel be developed. So, in order to This shows you in order to create stable discharge channel, what needs to be done. This is the concept which we developed. This is the Stark combustion. Stark represents for strong tumble and appropriately stretched, robust ignition channel. Stark for short. It's an acronym. So the Stark combustion is where you have a tumble in the cylinder. You have a strong turbulence in the cylinder, and when the piston rises, that turbulence will be maintained, and the maintained turbulence will carry the distribution, will allow for the extension of the distribution channel, discharge channel. There are two keys to this concept. First, and the left-hand side, when the engine intakes air, had to prevent the disturbance and maintain stability. And this central picture in the compression, the tumble flow is maintained without any bending. It's important that in the center there be control at the center of the cylinder space and make sure and maintain until the ignition point. With that, we'll be able to have stable combustion without disturbance. It's difficult for you to image, but 20 times, well, 20 times air is provided to the spark plug for every second. That is going to be the technology required. Next. So in actuality, how did we verify and design verify this Stark concept? As was mentioned earlier, what we want to realize is 20 times in same airflow being provided for each second. Make sure to maintain the stable discharge channel. We need to create strong flow and control, and then the turbulence needs to be adjusted and provide the same flow to the visualization engine. This shows you. This is a side picture from the in-cylinder gas flow. It's a simulation from the in-cylinder gas flow from the sideway. Left-hand side shows you the in-cylinder gas flow for the current engine, and the right-hand side shows the in-cylinder gas flow for the Stark concept. In the case of the current engine, the turbulence, when the piston rises, it disintegrates, as you can see. On the right-hand side, in the case of Stark concept, the airflow will stay in the center of the cylinder, and they're able to maintain even all the way to the compression. So as such, we verified whether or not this was assured. We carried out PIV visualization. We used PIV to verify results via the visualization engine, and the airflow was visualized as a result of the simulation. And you'll be able to find that the insulated gas flow has been verified. We're able to realize the outflow within the insulated gas through this design. Next. Then in the actual design, in the actual engine, what was the result? That shows we achieved 30% EGR high dilution combustion. This shows you the Stark high EGR combustion. On the top, we show you the net thermal efficiency, and the bottom shows the degree of combustion stability. Without, we're able to maintain EGR high dilution without working. As a result, we've been able to achieve 40%. The right-hand side shows the same engine. We carried out lean combustion and the results thereof. The top shows the net thermal efficiency, and the bottom shows combustion period. As a result, we were able to have, even with 2 times the airflow, we were able to maintain and achieve 46% engine thermal efficiency through the Stark combustion. And last but not least, this shows you the roadmap to achieve 50% thermal efficiency. So as a dedicated e-powered engine, on a standalone basis, we're able to have 43% efficiency, but we were able to have 45% thermal efficiency by combining with other technical development going forward in order to further improve thermal efficiency through lean combustion. On a standalone basis, we want to achieve 46% thermal efficiency, and this has also been verified. And because of if heat recovery is done, we believe that it's possible to achieve thermal efficiency of 48% down the road with improvement in battery technology. Based on total fixed point operation, we'll be able to improve the friction and compression ratio, which means that we'll be able to achieve 50% thermal efficiency. That is now within a possibility. So last but not least, we're very excited to achieve the highest level of fuel efficiency. We have a team of wonderful engineers who have consistently worked very hard to achieve this. I just wanted to point that out. So toward electrification, do we really need to further the IC technology, even against the electrification? There's some negative views, but we have experts in various domains as part of the team, and we constantly want to offer something better for the customers. We want to offer better fuel efficiency cars for our customers so that they'll have a more comfortable and fun driving experience. So that is the thought behind our development process. So as a result, we believe that we'll be able to fulfill the responsibility as engineers to enrich people's lives through technology. This is something that we have always endeavored to achieve. So that's all from myself. Thank you very much. Then we would now like to turn to the conclusion.
As I said in the beginning, with this e-power and battery EV, by using these two as the pillars by 2030, early 2030s, we would like to provide or do a new lineup offering at 100% in electrified vehicles. As I said, battery EV consists of evolution of battery and eco cycle. With this, we would like to embody or realize carbon neutrality. As I said, e-power is in the fixed operation with the further development engine. It will contribute to it will be another critical pillars to pursue the carbon-free society before the EV totally penetrates the market. In Japan and some of the Asia, e-power application has been widening. This fiscal year, we would like to widen the application in the segments as well as the regions. In order to apply more electric vehicles, it's not only about fuel efficient cars or CO2 emission reduced cars. We need to increase the attractiveness of electrified vehicles so that it's more convenient and more intelligent. We should always deliver new customer values. It says new driving experience. By using the characteristic of motor, you will feel as if your car is part of your body. Natural operation or manipulation will be possible, whether it's a full flat operation or the control system, which will never let the vehicle skid. And we unveiled e-Force in the motor show, and we are going to develop further on e-Force. As I said in the middle of presentation, we measure road noise while we ensure quietness of the cabin is the area where we continue working on so that the car will adapt to the circumstances, whether it's a passenger, driver, or environment. So it will be coordinating with navigation and learn the driving scenes. These are the areas of evolution that you can expect from us.
今日ご説
50% thermal efficiency technology. The presentation was pretty technical and maybe it was hard to understand. But the key message here is that this 50% thermal efficiency is to bring the ignition point of ICE to the ultimate. It's not very flashy or obvious, but without building up these fundamental technologies, we are unable to attain carbon neutrality. We are building up all these pieces of technologies. There's no magic here. We will continue developing EV and e-power, and together with carbon neutrality, we would like to reduce the CO2 throughout the life. Without COVID-19, we would have invited you to come to our lab to show you this 50% thermal efficiency, but because of these circumstances, we have to see you remotely. Once the COVID-19 settles down, I would like to create an opportunity so that you can really experience and see the object in front of you. And we didn't touch upon battery development today or eco-cycling. With regards to these subjects, I would like to create other opportunities to talk about it so that you can develop further understanding on what we are doing in order to pursue carbon neutrality, and we have the technical bricks to support us. Thank you for your kind attention. With this, we would like to end the session. Thank you for joining. Good day.